So this is an A-star program that on a grid with walls and everything. The A-star pathfinding algorithm, the variables involved in it, and the actual path. And you can generate mazes. You can move the start and end points, and you can really change anything in it. And I'm going to show you that. This is the program. As you can see, we have our start right here. We have our end, and these black things are barriers that we can't go through. Simple enough. And so when I press the return key, it will run the A-star algorithm, generate the path, and display it along with all of the other parts of the algorithm. So I've just pressed return here. I'm going to explain a little what this is doing. So what this is doing is so let's start at the very beginning, where the start would be. We have every cell has an F, G, and an H. G is movement cost, which is always 10 because 10 is the cost for moving from orthogonally. G is always 10 and is in lower left-hand corner. H is horizontal distance to the end plus vertical distance times 10. So right here, we're vertical plus horizontal distance is 28 times 10 is 280. And F, that's H, and is in the bottom right-hand corner. We have F in the top left corner, which is G plus H, and is the method of scoring a path or a node. And so the way A-star works is it puts the start into the closed list, okay? Then it goes through every node that we can reach from the start and puts that into the open list. It gives them F, G, and H values, and then it chooses the one with the lowest F, will start over. It adds everything it adds all of the nodes that are adjacent to the nodes in the closed list into the open list, and gives the nodes that we added into the open list parents inside the closed list. So that right here you can see this 1, 2 has a parent of the start, because that's how you get to here. You go from start to here. And then you look at the lowest F in the whole open list and put that into the closed list. And repeat the process. Add all of the nodes add all of the nodes that are adjacent to the closed nodes in closed list into the open list. Assign them parents, choose the one with the lowest F, add that to the closed list, and repeat. And we do that until we reach the end, which is right here, red 20,11. And then we found the path, and we backtrack the parents starting at the end. Because if we're going from, say, 0, 0 to 4, 0, then what we have is 4, 0's parent is 3, 0, 3, 0's parent is 2, 0, 2, 0's parent is 1, 0, and 1, 0's parent is 0, 0. So if we're trying to get from 0, 0 to 4, 0, the path will be backtracking the parents from 4, 0 all the way to 0, 0, which is what we do. I'm going to clear the blue stuff so you can see that when we backtrack the parents, it brings us up to the start, which is the point of the algorithm. And then the reason I did this is I do a lot of game programming, and when with game programming, you tend to have lots of monsters, and monsters need to have efficient ways of getting to the player, so that they can attack the player. Right? That's kind of a game theme, or a type of game theme. And so how will I'm going to clear the grid. How will a monster get from 2,11 to 16, or from start to end, with this in between? Previously, I had an extremely primitive method of pathfinding, or a couple primitive methods of pathfinding. One is go to a random square, a cell that we can reach from here, as long as it's not the one we just came from. It is extremely unlikely to lead to a player unless there are like 100 or 500 or 150 monsters in a grid this size. 21 times 12 is 252. Yeah, you need like 150 monsters for them to be able to get to the player. So one of the solutions is just go in the direction of the target object, which would take you this kind of path right here. However, once we get to 6,6, we can't go to, and we go to 7,6, we can't go to 7,7. That's a barrier. So what do we do? What does the monster do? The monster just sits and gives up, which really doesn't help the monster get to the player. So when I learned this A-star algorithm, I really was like, this will work well. And oh, here's an interesting one. It's impossible to get from the start to the end. So as you can see, it is going through everything that it can reach from the start, because since it will never add the end, it's going to go until the open list is empty. That's the condition. It keeps on reevaluating the open list, adding the lowest F to the closed list, and repeating until you add the end to the closed list or the open list is empty. If the open list is empty, then then there's no path. And eventually the open list is empty, and the algorithm has to admit defeat, as you can see here. And it's not really giving you the best path anyway, because there's no best path, you know. And so, this is a really smart pathfinding algorithm, and there's many things you can do with it. See, here's another one that it can't do. Oh, here's an interesting point. It's going down here, and now it reaches this cell right here. It goes down here. None of them end up being good, so they don't end up in the path. But now this cell has an F of, I believe, 180, and so does this cell, which means that it chooses this cell, this 180 right here. 170 is better, 180 is still okay, and it just goes through this thing until it can't possibly convince itself that it's a better path, and it goes back up here and goes through. And as you can see, it's it can't do anything here because currently it's not doing diagonals. And you can see here it's going to the only place the open list will let it go. Puts that into the closed list, it's the only thing it can do. Goes to the next one. So if we were to view the closed list, this would be every node here would be in the closed list. And my algorithm has a slight bias when it is choosing two elements with a equal f. It will always choose the element on the right, then the element on the bottom, as you can see here. It could be going this algorithm to 2, 5 or 1, 6, but it chooses 2, 5 because instead of continuing down here, it goes down here. So you can see it has a right down bias instead of a left up bias. And a bias can force it to explore on bad passages that look like they will give the same answer, but actually don't. And that causes the algorithm to run inefficiently, it's a whole field of study, like is there a way to figure that out? And as you can see, it goes to here. It's a horrible path, it never considers here. It just adds that to the open list. And so, as you can see, since it doesn't have F, G, or H, it never goes into the open list, and it never becomes part of a potential candidate for a path.